Welcome to the Here's a Summer of Programming Languages. Have you ever asked yourself, am I using a suitable programming language for this task? Then this collection of introductions to programming languages used in research software engineering has something for you.
Hello, my name is Magnus Hagdorn and I work in the scientific computing team at the Charité in Berlin. Today I'm going to talk to you why I think Python is such a cool language for writing research software. I'm going to talk a little bit about history, both the language and myself, and some use cases where I've used Python, and as I say, why I think it's particularly suitable. So ages ago, when probably dinosaurs still roamed the world, Python was developed. Well, actually, it wasn't that long ago. It was in the 1980s, developed by a guy called Guido van Rossum. Version 2 appeared in October 2000, followed shortly afterwards by version 2.2 in December 2001. Fairly early on, modules or packages for handling numeric data types appeared. First there was numeric and shortly afterwards numarray. They were similar but had different features, and they were both combined and provide the package NumPy, which is what we all use today. Then the scientific software stack was started in 2001. Scientific software stack, that is mostly SciPy, which contains routines for numerical integration, fast Fourier transforms, interpolation, and so on. Then another big addition was Pandas, that started in 2008. Pandas provides data frames a bit like R that give an abstraction that makes using Python or programming Python a little bit like a spreadsheet. So you've got tabular data that you can query and do computations on. It's very useful. Then Python 3 was released in 2008. That was a big change. It was backwards incompatible and it took everyone a little bit to catch up with it. And now Python 2 is well and truly in the past. So I got into Python in probably 2000 or 2001. At the time I was working on my PhD project, mostly writing Fortran code, but I also had to produce a lot of maps. For that I used GMT scripts. GMT scripts, or GMT has been around for a long time, and it's a bunch of scripts that produce PostScript output, or programs that produce PostScript output, and you tie them together using shell scripts, and you do computations using awk and bc and set. It's quite crazy. So I figured out, well, I can use Python for that, and it probably looks much nicer. So that's how I got started using Python. I then started using Python for pre- and post-processing, for my model runs, and obviously visualization. Still using GMT under the hood. Then I used Python for code generation. So for my Fortran program, I had to handle I/O, use netcdf for that, and that requires a lot of boilerplate to define the variables and open and close files. So I use Python to generate the code, fill in the boilerplate, and it reduced the amount of code I had to handwrite quite substantially. and made it a lot easier to maintain. After my postdoc, I worked partly as sysadmin, and obviously you need to write a lot of scripts there, and that's where Python comes in quite handily. And I also got into writing web applications, so that involves filling in templates, that's typically Jinja 2, and talking to databases. For that I used SQL Alchemy. So you can see there's quite a lot of variation what you can do with Python. It's not only scientific software, but all sorts of other stuff as well. To give you an idea of the width and breadth, I use Python for in scientific use cases. I tell you about two larger projects I worked on. So the first one is a system that we developed to measure plant productivity. So we strapped a bunch of spectrometers to drones, designed some software to open and close shutters, and obviously we needed software to control the recordings. It all ran on Raspberry Pis, and for the software I developed, and that was a client-server architecture that could be remote controlled via Wi-Fi and a web interface. And I also worked on another project at the different end of the scale. Here we wanted to process huge raw satellite data, and we had to regrid the raw data, which is a big data problem. We had over a terabyte of data, and we used Python to do the processing, and used Archer 2, which was at the time the national supercomputer in the UK, and I used thousands of core to do the processing. Okay, so that's a bit of the historical background. And so why Python? To start with, it's open source and it's free to use, and which means that it doesn't matter what hardware you use or operating system you use. You can just download it, install it, and start to use it without having to worry about license or paying for licenses, and you can just get started. It's a general purpose programming language, so it was designed to solve sysadmin problems, and later on scientific support for scientific workloads were added, which means basically you can use it for all sorts of problems, which is great. Then there's usually one obvious way of solving a problem. So Python is quite opinionated, and I think that's a good thing to constrain how you solve your problem. You don't have to choose from many approaches. It's good for gluing stuff together. So if you want to control models, you can use Python. You can use it for writing workflows. Comes with batteries included, so I'm going to talk about that in a moment. It's easy to learn, and it does not need to be compiled, which reduces the friction of trying stuff out. It has a rich ecosystem, and it can be easily extended and embedded. So that means you can either stick it into other programs, or you can add new functionality to it. And you can do really cool stuff. So I'm going to expand a little bit on some of those items here next. So it's easy to learn. To start with, there's very little syntax and punctuation. So this is an example loop over a list, and you can see there are not many braces or special notations, and it reads a little bit like plain English. So that's really great. And there's this read, eval, print loop, REPL loop, which means you can interactively enter some code, press return, the interpreter evaluates your input and prints out the result. That's really great for trying stuff out. And so typically when I program, I've got an interactive Python shell to hand where I can try stuff out. And then you copy and paste that into your program. It's a multi-paradigm language, so you can start off with writing a plain script. So that's probably what many scientists start with. You read some data, you do some processing, and then you plot the results. You can also use it for procedural programming. So that means you refactor your script and extract the useful bits and put them into a function. And you can collect those functions in modules and packages so you can reuse your code. And that's quite a traditional approach that is similar to what you would do in Fortran or C. You can also program Python using an object-oriented paradigm. So you can define classes with open recursion, inheritance, dynamic dispatch, and so on. All the good things that you would expect from an object-oriented programming language. Finally, it has also some functional programming approaches. So you can mix and match these things, and the big thing there is it allows you to grow. So when you start off, you probably start writing scripts, and as you get more proficient at the language, you can refactor your code and into functions and packages. And when you start writing a bigger project, you can use objects to split up the work. Another really nice thing is that Python has support for mathematical computations. So, for example, if you want to square a matrix, you multiply the matrix with its transpose. And in Python, there's a special operator for the matrix multiplication. And it looks pretty much like the code the notation that you will find in a paper. So that makes life quite easy for scientists. Batteries included means that there are lots of really useful packages, so you don't need to start developing from scratch. I've picked out some packages that are particularly useful. Obviously, there are many more. So to start with, I picked requests, which is a package that allows you to connect to web services and download data, and you can use it to do REST API calls. So very handy. HiRSE is a package for developing graphical user interfaces. It is based off Qt, which is a cross-platform open source GUI toolkit, and it allows you to create beautiful user interfaces that will run on any operating systems. So it's really cool. The next one, SQL Alchemy, is an abstraction on top of database packages. So you can use that to talk to small SQL databases such as SQLite, or to big database systems like Postgres or MySQL. And if you don't want to write SQL code, you can also use it as an object relational broker. And you define your database using Python classes, and SQL Alchemy will handle creating the tables for you and doing all the interactions with the database. Obviously, sometimes this abstraction comes at a cost, and it doesn't always produce the best possible SQL. In those cases, you can still write raw SQL if you want to. So next is maybe a bit more sciencey. So for machine learning, you can use TensorFlow and PyTorch, two widely spread packages that will make use of any GPU accelerators that you might have. Another big topic for scientific programming is handling big data sets. That's where X-array comes in. X-array can be used for multidimensional grid data, and it can handle big data sets with many terabytes in size. So I already talked about pandas. If you have to handle big data sets using pandas, you can use Dask, which allows you to do parallel computation on pandas data sets. The final package I picked out, Phoenix, is for finite elements. So there you use Python to define your partial differential equation and what sort of elements you want to use, and the code will generate all the bits that you need and call big C++ libraries under the hood and allow you to do big simulations using very little code. Okay. So next I want to talk about the rich ecosystem. So to start with, you can choose from a whole bunch of different linters. Linters allow you to ensure that you stick to certain conventions. I picked out, so personally I use Flake 8 a lot. And if you want to automatically change your code as well, you can use Black. There's plugins for your programming editor. So personally I use Emacs, but it will also work with Visual Studio or PyCharm. There are a whole bunch of different testing frameworks. It seems that PyTest is a particularly good choice these days. PyTest allows you to run unit tests. You can combine that with hypotheses, which will generate numeric input for your functions. The other aspect is documentation. So you can use Sphinx to document your APIs and generate beautiful HTML documentation that is then generated and displayed on services like Read the Docs. Sphinx is used by projects like NumPy or Python itself. So it's a good thing. The next bit is Jupyter Notebooks. Jupyter provides a web interface to different languages, including Python. And notebooks are a way of combining documentation with live code and result. results. It's a really nice way of getting into programming and is very suitable for script type programming, which is, I guess, a lot of what scientific programs look like. The next step up from that is reproducible documents. So you can use Quarto to produce beautiful PDF documents from notebooks that you write with special markup, and you can produce publication-ready documents. Okay, so that's a bit of the ecosystem. Next is I'm going to talk about extending and embedding Python. So extending is you sometimes there are no suitable packages for Python available yet. So for example, if you want to talk to a particular bit of hardware, you can write your own C extension for that, and it's not that difficult. There's a nice documented API, and you can make use of the numeric data types provided by NumPy in your C extension. And so another good thing about writing C is that can be embedded into a whole bunch of other languages or interface to a whole bunch of other languages. For that, you can use Swig, and Swig will produce Python interfaces to your C modules. The other way around is you can embed Python interpreter in bigger projects. So for example, Blender and ArcGIS use Python as their scripting language. And more recently, even Microsoft Excel allows you to embed Python code in your spreadsheet. So finally, you can do also really cool stuff using Python. So the example here is a microcontroller that comes with Wi-Fi and a whole bunch of GPIO pins where you can attach sensors to it. And you can boot that straight into MicroPython, and you can write your firmware for that microcontroller in Python. It's really super nice. Those things are not too expensive and a great way of exploring physical computing. So that's it from me. And next, Renato will compare Python to some other programming languages. Thank you.
Hi everyone, I'm here today to talk to you about Python for research software development, and I'll be focusing on the language and some of the not so great parts, but at the same time giving possible directions to overcome some of those. My name is Renato Alves. I'm a senior bioinformatics community manager at EMBL Heidelberg in Germany. And before I get started, just a little bit of background about myself. So I am a software developer with Python for close to 20 years. It was not my first programming language, but it was definitely the one that stayed with me for the longest, and the one that I truly appreciated on many aspects. I have tried many other languages over time, R probably being the one that I use the most, and then also Haskell, JavaScript, and many others, and shell script as another type of glue. I'm also an open source contributor for almost as long. Many of these projects were created or that I contributed to explore different features of either the projects themselves or features of Python. So they were in some ways also playgrounds. And these are not in my research space, but they were things that I was just exploring on the side or in my free time. More in my work side, I've developed different kinds of databases, websites, many of them built with Django, a popular Python web framework, and some of them of different scales, from just a small web interface to run an analysis tool, but also a complex website that took years to develop. During my PhD, I also did some big data efforts, big computation efforts, and at the time we were using a tool that was developed in-house called Jug, and I created this Jug schedule system, which expanded the functionality of Jug and made it a bit more integrated with different clusters, high-performance computing clusters, namely Slurm. This project is now essentially unmaintained, but the link is still valid for reference. So in short, I've been involved with many different types of efforts with Python, web development, also a lot of data analysis. I'm a huge fan of automation, and I do quite a bit of system administration and infrastructure maintenance for where I use Python quite frequently. So now focusing a bit on the good side of Python. So Python is very popular, and this is a very known fact. It is widely used and praised, and it has always been in the top of the charts. Here we can see the top programming languages on GitHub, according to their own statistics. And you will notice that in 2024, Python actually made it to the first spot. This is largely driven by the fact that one of the most popular AI frameworks, in this case TensorFlow, is built with Python or using Python as the primary language, and so this has been driving the more recent popularity spike. It is at the same time one of the most user-friendly languages that at least personally that I have used, and I particularly appreciate the errors, which are one aspect of many languages that tends to be underappreciated. Where in my case, it is probably the most common thing that I deal with, and it enriches my debugging, my troubleshooting experience. Just to give an example, in recent Python versions, there has been also extra care to improve the quality of the error messages. Here we have just a couple I highlighted, but you can see that they now carry much more context, much more information. And so this shows that the Python core developers also care that the messages are as useful as they can be, and to have the language help the programmer as much as possible. Now, some of the not so great things, or some of the bad things. Python has not been free of criticism, like many other languages, of course, but some of these points are quite valid. So one thing to clarify is that Python, when usually we refer to it, it's both Python a language, but also the interpreter, which serves as the reference for the language itself, in this case, CPython. But Python the language has many different interpreters. So you can, for instance, run IronPython and so on, that allows you to, for instance, connect with other languages by running these interpretations inside. One of the downsides here is that as the language is evolving together with the interpreter, oftentimes if you want a new feature, the only option you have is to upgrade the language and to upgrade everything, which might mean that your code base will either have to wait for the transition to that, or you will need to consider what would upgrade mean to your project. And there have been some difficult periods in the past. So one of the most known is the transition to Python 2, from Python 2 to Python 3. The syntax didn't actually change much, so the language itself didn't change much, but the interpreter had some significant changes internally that led the Python core developers to make a major digit change. And whenever this happens, unfortunately, it was a lot of effort to make a transition of the code bases from 2 to 3, and some of the software never actually made it out of 3. Python 2.7 officially died in 2020, there are already other runtimes like PyPy that still support it. Another criticism is that Python is slow, or CPython in this case. This is, however, something that the core developers are aware, and they have been doing improvements for. One of the most recent ones that it's still rather experimental, I would say, is the removal of the GIL, or the global interpreter lock, which has been something that hindered whenever you're trying to run code that runs in multiple processes or threaded code. The threaded model in Python has always been a little bit different from what you might expect if you've used threads in other languages. But this is also, of course, allowing additional gains where with some occasional trade-offs. You might still say, well, even after all this, it's still slow. So if your code is particularly heavy on numerics, you might want to consider tools such as Numba, Python, JAX, or even Cython, which allows you to connect with C more directly. These are just-in-time compilers or C interfaces that allow you to get closer to machine code, and of course get that gain with obvious trade-offs of code complexity. Many of these, they only implement a subset of numeric or NumPy-like interfaces. But one of the downsides is that if you want to have the experience of Python as a language, when you start using these tools, you quickly feel like you might be using a different language, because either the syntax is different or the way the interfaces work are quite distinct as well. And I'll get more on this in a bit. Now, some of the more ugly parts, or the pain points. So backwards compatibility is always difficult. And in Python, I would say it's mostly okay, but occasionally there are some sharp corners. And these are mostly to do with internals of Python. From the surface, I would say that things are relatively stable. Another form of backward compatibility that tends to get a little bit more challenging is dependencies. I'll get more into that in just a couple of minutes. Another pain point is that sometimes the language evolves quite fast, and usually it evolves in ways that are optional. So for instance, a new typing syntax has been introduced in Python, and this is optional. But as we will see later, this does look like a completely different language from a language point of view. Then different semantics as well in the language. You might have seen the yield from syntax that was present around Python 3.3, coroutines in Python 3.4, and then in 3.5, async and await keywords were introduced, which sort of obsoleted yield from, or at least some of the use cases that the initial ones were created for. And then in Python 3.10, there were some semantic restrictions around yield from and coroutine, because there were some backwards incompatibilities that would have to be introduced to allow, for instance, the typed Python to work as expected. Now, one of the most painful points at the moment with Python is actually packaging. So packaging is essentially making your code available in a form that is also easily installable by others. The packaging itself is not difficult, but there are many options to choose from and many different formats to navigate. This used to be more complicated. Things are improving a lot. But there is one aspect of packaging that is particularly hard, not because of the packaging itself, but because of dependencies. And dependencies are getting increasingly more complicated. As Python is a dynamic language and it's not compiled, this often means that dependencies, they either are heavily tested, and this would be, for instance, your responsibility as a developer when you integrate new dependencies in your project. But oftentimes, because the quality of these dependencies can vary quite widely, it is sort of comparable in experience to having spaghetti code in your project. And so oftentimes the recommendation is to have integration tests and other kinds of tests to make sure that the dependencies aren't suddenly changing in ways that you didn't anticipate or introducing bugs that you didn't expect. If you have very large dependency trees or graphs, then this often spells trouble. If you have any kind of GPU computation or CUDA dependency, brace yourself. Not because the packages themselves are particularly tricky, but because the way you would need to install and the different components that you might need to install may have a lot of incompatibilities with different systems. And so to get the right combination of versions to work for your environment may prove more challenging than one would initially expect. And this is a particular pain point for the final users, which have to install this on their own environments. Now, other pain points that are more like not a bug, but it's a feature type of situation. So Python is a language, and a language being an interface, it sometimes looks like and using this analogy here, it sometimes looks like a bike, but it kind of drives like a truck. But depending on the library, it might drive like a speedboat, actually. And so one of the aspects of the language is that it is possible to create domain-specific languages out of it, or to overload the Python semantics. And so when you have different libraries, they might actually feel very different, or the way you interact with them might be very different. So while you might have Python as one language to interact with it, for each library, you might have a different mental model. So the more libraries you have, the more mental models you might need to use. To give one example, in base Python, so in the standard library, equality typically means are these things equal or not, in the sense of equality of the word. And so if you try to compare things with a double equal, you can see that you get a Boolean answer out of it. And in fact, if the second line here, what it's showing you is that the equals is just syntax for another function that is internal to Python that has these double underscores around, also called dunders. And so this is another way of, this is just showing how it works sort of under the hood. And the reason why I'm showing this is because once you understand that this is a function running underneath, you can imagine that if you change that function, you can change the behavior of what this code is doing. And so, for instance, in other libraries such as SQL Alchemy, the double equal sign in this case doesn't actually do an equality comparison. As you can see here, it actually is used to construct part of the statement in SQL, and in this case to create a comparison between a column and a value that is specified in the SQL statement. Another aspect that can be quite challenging is that I mentioned earlier that Python introduced typing annotations, and these can look very different. And not only that, but the typing syntax has been evolving in different versions. And so while type annotations are not used by the CPython interpreter, meaning that Python isn't actually do internally any kind of type checking, you can use these annotations by external tools. And here I'm also highlighting one perhaps not so known feature, is that one of the static typers, MyPyC, actually has a C compiler inside. So if you annotate your code and you use this MyPyC, you can actually compile it and gain some extra speeds. So this is a good motivator for having annotations, and you can potentially benefit from some performance gains. But why am I mentioning typing? Because it does look very different, and if you're not used to that to that syntax, it might take a while. So if you're used to Python 2 or the original initial Python 3, this is what a typical function would look like. And as of Python 3.5, there was some typing annotation that was introduced. And more recently in Python 3.10, the syntax was changed a little bit. So optionals are now represented by a vertical bar to represent an OR operation in terms of type annotation. And as you can see, just comparing these three, they do look quite different. So one could even not recognize, especially the latest one, as being Python. One could think that it's a slightly different language when in fact it's not. I should say that although this was introduced in Python 3.10, you can still use the code as it's in the first column with Python 3.10 and recent versions. That is what having optional type annotations implies. But as you might find that the code uses a mix of these styles, because you might have code that is type annotated and code that is not. Here, linters and other tools might help ensure some consistency. Now, another aspect is on the philosophy and the community of Python. So Python has had for a very long time this Zen of Python included in the code. I'm not going to read through all of it, but you can see how a lot of the aspects of the language are sort of embodied in this text. So things such as everything in Python is an object. Almost all of the syntax that you see translates to these dunder methods that I mentioned before. There's a lot of good humor and Easter eggs. You might want to try to import anti-gravity to get another one. And each library is a bit of a different community, and some are more welcoming than others. If community is something that you don't usually worry about or think about, you might want to consider that there might be a library that you actually want to use, and then you notice that, oh, the last commit was 4 years ago, and you check the open issues and you find lots of questions asking if the library is dead. Similarly, if you're programming alone, you may wonder, okay, who do I ask for advice? Who do I ask for guidance? We do have AI now, but luckily there are still some spaces that one could reach out to. So here linked the Python community space in the Matrix network. And if you think, why should I worry about language philosophy? So this touches on things such as if the language is compiled or is dynamically interpreted. You can have, for instance, runtime errors that you haven't considered, you haven't tested. In compiled languages, oftentimes these are caught at compile time. So that this is also a trade-off, but one that impacts what the language does and how it behaves. Static checkers and linters can of course be of help here to improve that aspect. Some languages have the practice of giving warnings, and oftentimes warnings for things such as everything is fine, but you do give warnings anyway. That can be desensitizing for the end user, and it also tells you something about how that language philosophy goes. Whereas on others, you might have languages that try really hard to not give you any false impressions. So even if there was some kind of critical error internally, they will try their best to not crash, to not die, and so this is not so much the case for Python, but you can, for instance, use a general try except patterns around your code to make sure that any exception is handled and not passed on. If you have features that you are looking for in another language, you might also consider interfacing with it. Here, Python doesn't restrict it, so you can use things such as C types to interact with other languages. And if you consider that tooling is not particularly important, well, you might find that if you're still debugging by using print statements, having a debugger could be of help. And if you've ever tried to install software with Conda and with a complicated set of dependencies, the dependency solver and how long it takes to run, that has been a pain point for many users. So these are another aspects to consider about what is valued or what kinds of philosophies a language or its ecosystem follows. And so now quickly, what to look for and what kinds of alternatives one could consider. So just very briefly, in Python, as we mentioned, simplicity in the large ecosystem are some of the positive points. Then we have on the downside, possibly slower performance and packaging and dependency struggles. If you consider languages such as Julia, very known for numerical computing, very considered friendly for scientists, has a smaller ecosystem and some issues with slower startup time, mostly because of the just-in-time compiler that needs to kick in. Are excellent for statistics and data visualization, very rich ecosystem for academic research, has quite some inconsistent syntax across packages. The most known is the variation that happens between base R and, for instance, the tidyverse ecosystem of packages. And it hasn't really made it outside of some niche areas. So as a general purpose software development language, it's a little short. Then languages such as Haskell, it's quite different. It has a very powerful type system, has a very sophisticated compile time error catching, There's often the saying that if code compile, it most likely is correct. This is not entirely true, but it speaks a bit to some of the efforts that the compiler tries to go to indeed make sure that your code is correct, even mostly from a typing or from a syntactic point of view. It has, however, a very high learning curve, and it's quite academic software, so it has not so much penetration in the job market. But if you want to see cool concepts, a lot of them came from Haskell, and many other languages have borrowed from there. Rust, for instance, being one of them. Rust is a system-level language, very high performance, sort of C comparable or C++ like, strong memory safety, also very steep learning curve, and quite verbose for some tasks. Java, you probably know a bit of it. It's quite mature. It's still used in many fields. Image analysis, for instance, being one of the ones for the longest. Fiji, ImageJ, and such tools have been long-standing. If you work with it, it has a verbose syntax and a rather heavyweight runtime. Go, not so much in the research space, but it's simple, readable. It has quite some interesting features, and it has quite a niche space also in the web development area. It has some limited ability to use generics, but things are improving, and some limited abstraction tools. And then JavaScript as the counter in that initial list that we saw of top languages. It runs everywhere, browser, command line. It has quite a good asynchronous and event support. It's quite popular, mostly because it runs in the browser, so you can do a lot of cool things with it. But it has a lot of inconsistent behavior, and this can be off-putting. And if you want to have the safety of typing, then you need to use TypeScript instead. So in summary, Python, easy to learn, multi-paradigm, and not crazy different from others. It has a huge community with a wide range of scientific domains, a wide range of high-quality libraries as well to pick from. Many tutorials and learning resources abound. One good one to go to is all the carpentry lessons on both data and software development oriented. And some of the cons, if performance matters, you probably need more than just bare Python, which is, I would say, what typically happens anyway. If you do numerics, no one recommends to use just Python. You most likely get NumPy as the first suggestion. Then many large communities, but often fragmented, sometimes by topic, sometimes by library. Many domain-specific languages, interfaces, and you might need some flexibility, mental models, because each library can have its own way to do things, and each also with its own learning curve. And the typing support is still getting there. There's a lot being added, but you might need to get used to that new syntax. And that's everything that I have. So thank you very much.
Thank you for watching this introduction. Please check out the slides on Zenodo, linked below, and see you next time.